Hello everybody, this is Michael. In this video, we will talk about the I2C Byte write coding 01 for FPGA driver I2C EEPROM. So from previous video, we have this code. Okay, so it generates the I2C clock is here, generates the I2C clock. This code is this module is I2C driver module. This code is I2C driver module. The first things we will edit all the signal, all the interface signal for this module. So here we already have the input clock. We have the input reset. We need to edit the input enable. The input enable is here. We added the input enable. We need to edit the down output signal. The down output signal, we divided it as a reduced value. Okay, so this is output signal, reduced. Okay, so next is read or write input signal. Read-write input signal is here. So this is a read and write input signal. Next will be the address read and write input signal. So we define the input signal, address, read and write. Next is data, read and write data. Here is the data. It's all 8-bit. Next, this is the write data. This data will write into the EEPROM. This data will write into the EEPROM. You will see this is the input data. This data is read out data. This data is read from the EEPROM. So we define the read data. Okay. So this is output reduced. Is the read data. Read from the EEPROM. This is write into the EEPROM. This is address. This address is for write and is for read and write. Okay, so which address we need to read or write from the EEPROM. Okay, so this side is clock, I2C clock output, and here this is data. We already have the clock. So what we need to do is data. Okay, this data is the input and output type. Input and output type. You will see here. So this should be like this. Okay. This is input and output type data. So it is one, the I means input, the O means output. So for this one, it is input and output data. Okay. So the next things we will define the state. Okay, So from previous video, we know for the right coding, we have the nice state like this. Idle start, device address, acknowledge word address, acknowledge data, acknowledge stop. So next things, we will define the nice state. Okay, so let's go back. So we save it first, save, and then we go down here, and then the first things we need to define the current state and the next state value. We will divide it here. Okay, so this is the current state. This is the next state. So next, we will define the state name. So we define like this. We use the local parameter to define it. So you will see here, this is idle, start, device address, acknowledge 1, word address, acknowledge 2, date, write and read, acknowledge, and stop. So this is for byte write status. Okay. So you will see I define the current state as from 0 to 13 is 14. Is 14 state. I leave some state for the read state. Okay. Currently here is for the write state. So in the future we will add the read state here. Okay. So this is a state define. So next we will focus on the state switch. Okay. This is a state machine. So next we will focus on how we switch between the states. Okay. So we use 3 always block for the coding. The first always block always like this. The first always block is always like this. Okay. So current state always will be idle state. So the current state will switch. Next, the current state will switch to the next state. This is the first always block. Next, the second always block like this. The second always block will switch between the state machine. Okay, it will be like this. Okay, let's take a look. So this is the second always block. So it is here the current state. If the current state is idle, we will match here. So this is idle. If this one is idle, we will check the enable input signal. The enable input signal, which is here. The enable signal is here. So we check the enable signal to see whether it's 1 or not. So when it is 1, means we start the write processing. When this one is 1, we start the write processing. The next state will go for the start state. So it will be here. When it is 1, next state will for the start state. When it is 0, when it is 0, it will stay into the idle state. It will stay into the idle state. So this is for the idle state. Okay. So next, start state. Start state. Here we will output the start B and then go to next state. So for this state switch, we will judge the clock negative edge. The clock negative edge means we finish the 1 clock or not. As we know from previous video, we know this negative edge is this position. So it is the end of 1 clock. So this is the start of 1 clock. The negative edge is here. So it is from here to here. And we will, at the end of the I2C clock, 1 clock, to switch to the next state, because the start B, this start B, need 1 clock, at least need 1 clock output the start B. Okay, so if the clock is still inside the 1 clock, we will stay into the start B. We will stay into the start state. Okay, so next, so after the start state, we will go into the device address state. Device address write state. In this state, we will write the device address out. In this state, we will write the device address out. So check here. So this is device address. It will need 8 clock. 1, 2, 3, 4, 5, 6, 7, 8. It will need 8 clock to output the device address. Okay, so we give 1 bit count equal to 7. So this bit count to calculate how many bits here. Why it is 7? Because it starts from 0. This one will start from 0. So we also need to define this variable. We define this variable is here. Okay, we define before this one. Okay, so this is a bit count. Okay, so this is a bit count. It from 0 to 7, totally 8 bit. 8 bit. Okay, bit count for the data buffer. Okay. So we stay here. So it needs 8 bit from 0 to 7 to output the device address. 8 bit output the device address. This start is 1 I2C clock. This device address is 8 I2C clock. Okay, so this means this one means finish 1 I2C clock. Okay, this one means finish 1 I2C clock. It is 1 I2C clock is this position. Okay, so next, here we output the device address, and then we will go into the acknowledge 1 acknowledge 1 state. We will go into the acknowledge 1 state. In the acknowledge 1 state, we still need to check the I2C negative edge, and also we will check the clock error. We will check the acknowledge error variable. We will check the acknowledge error variable. If the acknowledge error equal to 1, it will go to the idle. So if it is 1, we go to the idle. If it's not 1, we go to the next state. So this state is word address. Okay. If it is 1, we go to the idle. If it is 0, we go to this state. Okay. So otherwise, we will stay into the acknowledge 1 state. Okay. So we also need to define this acknowledge error variable. We define it as 1 register variable. We also go back here. Okay, we stay here. Define the variable here. So this is acknowledge error flag. Okay, is a register variable. Okay, let's go back. So it's this position. From this position, from this state, if no acknowledge error, we will go to the word address. Okay, word address state. Word address state is here. So this is word address state. For this state, we will output 8 bit. Okay, 1, 2, 3, 4, 5, 6, 7, 8. We will output 8 bit word address. So we will still use this bit count variable to check whether we output the 8 bit or not. From 0 to 7 is 8 bit. So this is also means finish 1 I2C clock. Okay, this means we finish 8 I2C clock. Okay, so if we finish this one, we will go to the acknowledge 2 state. Okay, acknowledge 2 state is here. The acknowledge 2 state. The acknowledge 2 state will check the acknowledge error variable. If no error, we will go into the date write and read. This one is write processor. Okay, this one is write processor. And if there is some error here, we go back to the idle. Otherwise, we stay into the acknowledge 2. Okay. So for the date write state, we will output 8 bit date. Okay. For the date write. So this is this state. We will output 8 bit date. 1, 2, 3, 4, 5, 6, 7, 8. We will output 8 bit state. This means 1 I2C clock. This means 8 I2C clock. And then we will go into the acknowledge 3 state. This acknowledge 3 state, like the others, we will check the acknowledge error flag. If no error, we go to the stop state. If there is some error, we go to the idle state. For the stop state is here. For the stop state is here. Okay. The stop state also need one I2C clock. Okay, one I2C clock. So in the stop state, we will output the stop B and dump B, and then we go to the idle state. So if less than one I2C clock, we will stay in the stop state. Okay. For the default state, we go into the idle state. Okay. So this is state switch. This is the state switch for the state machine. This is the second always block. Next video, we will talk about the third always block. So in the third always block, it will handle every data output and data input. For example, how we output the start B, and how we output the device address, and how we output the word address. Okay, so this is I2C byte write coding 01. In this video, we focus on the state switch. Okay, state switch. Next video, we will focus on the state function, state how we output data in each state. Okay, so this is Michael, and see you next time.